we have got one equation, the differential energy balance equation for internal energy and kinetic energy. What we will now do is we will derive a separate differential energy balance equation for kinetic energy, so that we can subtract that equation from this equation. Okay. And so, we are proceeding towards deriving a differential energy balance equation for kinetic energy. I said separate equation, the reason is that this equation I would say comes parallelly, not sequentially from the previous equation, which means that the starting point for this equation is different. The starting point is the linear momentum balance. Okay, so let us write the x component of the linear momentum balance equation, and let us see how do we derive the differential energy balance for kinetic energy from the linear momentum balance equation. Okay. So, that is a linear momentum balance equation in the x direction, the transient term, the convection term, and then we have the body force term, surface force due to pressure and viscous stresses. Now, as I told you, the derivation of differential energy balance equation is easier if we express the equations in terms of substantial derivative or from the material particle viewpoint. So, we will express the left hand side in terms of the substantial derivative of velocity multiplied by density, which I have already done. Right hand side remains same. So, linear momentum balance equation from an Eulerian viewpoint, this is from a Lagrangian viewpoint. Now, we have just now discussed that we have neglected the work done by viscous forces. So, in the linear momentum balance equation also, to proceed further, we will neglect the viscous forces on the right hand side and keep only the body force and the surface force due to pressure, so that it is in line with our assumption. So, let us write down that linear momentum balance equation excluding the viscous forces on the right hand side, and that is nothing but our Euler equation. So, we have taken the linear momentum balance equation expressed in material particle viewpoint, neglected viscous forces, and we have got the Euler equation. Now, what we will do is multiply by Vx on both sides. You will understand why do we do that shortly. Multiply by Vx on both sides. So, we have Vx rho dVx by dt is equal to Vx rho gx minus Vx dou p by dou x. Now, this equation can be expressed as, the left hand side of this equation can be expressed as d by dt of Vx squared by 2. Why is it? If you take d by dt and then let us say you have half here and we have Vx squared, and now if you differentiate you have 2, then 2, and then we have Vx, and then we have d Vx by dt, and that is a term on the left hand side, of course multiplied by rho. So, when we multiply the equation by Vx on both sides, the left hand side can be expressed as rho into d by dt of Vx squared by 2, and of course right hand side we have the terms Vx rho gx minus Vx dou p by dou x. Now, let us repeat the exercise for the y direction and z direction, multiplying by the respective velocity components. Okay. So, rho dv y by dt is equal to rho gy minus dou p by dou y, and we multiply by Vy on both sides, and that is of course not shown here, and then we get an equation similar to this. Okay. Similarly, in the z direction as well. Also like to mention, we multiply by Vz on both sides. So, it is multiplied by respective velocities, so that we get here Vx squared by 2, here we get Vy squared by 2, and then Vz squared by 2. So, now Let us write down the equations which I have derived in the previous slide in all the three directions. Now, you can slowly start recognizing that V x squared by 2 is one part of the kinetic energy. So, if you sum all these equations, what we have is V x squared plus V y squared plus V z squared, which is nothing but V squared. We have a half there. So, which means we have got the kinetic energy on the left hand side. That is why we multiplied each equation by the respective velocity component. So, if you sum, the left hand side becomes rho d by dt of V squared by 2. That is what our objective was. Our objective was to get a separate equation for the kinetic energy, and so we have got now a differential energy balance equation for kinetic energy, because the left hand side is rho d V squared by 2 by dt. Okay. Now, the right hand side, this term has been expressed here, rho into g x V x plus g y V y plus g z V z, and then all these three terms have been expressed here as minus of these three terms, V x dou p by dou x, V y dou p by dou y, and V z dou p by dou z, and what is shown here is V squared as sum of V x squared plus V y squared plus V z squared. Now, to proceed further and to make our derivation convenient, we will take this term and express it as a sum of two terms. Okay. What do we do? Take the term highlighted in blue and we will express in a form which will be convenient for further steps in the derivation. Let us do that, and then I will explain what is that we have done. Of course, it should be obvious to you if you look at it. Okay, what is that we have done now? Use the product rule. How did we use the product rule? We know that dou by dou x of P V x is equal to P dou V x by dou x plus V x dou p by dou x. What we have on the left hand side is V x dou p by dou x. This is a term on the left hand side, and that we have expressed as dou by dou x of P V x minus P dou V x by dou x. That is all we have done. Okay. And similarly y direction, similarly z direction, and now we have grouped these terms here and then grouped rest of the terms as the second term. Okay. And so, let us substitute them back here. Of course, here you have a minus here. So, left hand side is of course same, right hand side this term is same, right hand side instead of this term we have now got two set of terms, that is minus of this and then plus of this term. Okay. So, just substituting this on the right hand side of the this equation. So, now this is our equation for the, this is the differential energy balance equation for kinetic energy. Now, what we will do is look at the physical significance of each of the terms here. To help us to look at the physical significance of each term, we will re-express this from an Eulerian viewpoint. Just to help us, I recall a slide which we just now did. What we did was we had derived the differential energy balance from a control volume point of view or a Eulerian point of view, and we did these steps. On the left hand side was expressed from a particle viewpoint, or we express the same equation from a particle viewpoint, and the left hand side was in terms of the substantial derivative of the total energy per unit mass. So, now the left hand side was from an Eulerian point of view. We did a series of steps and expressed in terms of the substantial derivative. The situation what we have right now is the reverse of that. We have already the differential energy balance equation, the left hand side of that in terms of substantial derivative. So, we like to go back here and express in terms of the Eulerian viewpoint. Okay. So, let us look at the next slide, then you will understand. Okay, that is the differential energy balance equation for kinetic energy. The left hand side is in terms of the substantial derivative. We express that the left hand side in terms of the transient and then the convection terms. Okay, that is a transient term and then the convection term. So, this equation, the first equation is from a material particle viewpoint or Lagrangian viewpoint. The second equation which is being written now is in terms of the Eulerian viewpoint. Let us complete. We will also go back to the previous slide and once again explain what we have done. Okay. What is that we have done? I would like to quickly recall, quickly repeat it. We have got the equation for kinetic energy with the left hand side in terms of substantial derivative. What we are doing right now is just to get a physical interpretation for this differential energy balance equation, that is only objective. Okay. Now, earlier when we did for the total energy balance equation, the left hand side was in from a Eulerian point of view, we expressed that in terms of Lagrangian point of view. So, we went from let us say dou by dou t, dou by dou x, dou by dou y etc. to capital dE by dt and multiply by rho. What is it we have right now? We have already the substantial derivative of kinetic energy per unit mass. We like to express back in this form. So, if you have this form, how do you write? It is rho and then d by dt of E. What is that right now? We have rho into d by dt of V squared by 2. So, now we have to just go back and write dou by dou t of rho into V squared by 2, dou by dou x of rho V x V squared by 2. Okay. That is what is written here. See, rho by dou t of rho V squared by 2, dou by dou x of rho V x V squared by 2. So, we have gone in the reverse direction. This once again want to emphasize this is done just to look at the physical significance of all the terms in the differential energy balance equation for kinetic energy. We will not carry forward the derivation using this form of the equation. As I told you, the convenient form for derivation is only the Lagrangian form of equation. Okay. This we have already seen. Okay, now let us look at the significance of each term. Left hand side, the terms are familiar to us. It is time rate of change of kinetic energy per unit volume. We have come across earlier mass, momentum, then total energy. Now we have come across kinetic energy. What is the next set of three terms represent? They are the convection terms. So, they represent net rate of flow of kinetic energy out by convection per unit volume. We have seen this earlier for mass, momentum, total energy. Now, analogous meaning for kinetic energy. Now, let us look at the right hand side. we have already seen the significance of this in detail, tells rate of work done on fluid by gravitational force per unit volume. Now, we have also seen the significance of this term, that is net rate of work done on fluid by pressure forces per unit volume. Now, the last term is something which I have not come across. We will just write the significance and then few slides later we will justify the significance. It just tells you that rate of conversion of kinetic energy into internal energy per unit volume. We will few slides later we will discuss why this term represents this physical significance, which is conversion of kinetic energy into internal energy. What this equation tells you is that the kinetic energy can change because of all these factors. That is the overall concept which we can take from this equation. So, the terms are all analogous to any conservation equation, the transient term, the convection term on the left hand side, and then we have rate of work done by gravitational force, pressure force, and there is a term which tells about the conversion of kinetic energy to internal energy, which we will discuss little later. Okay. We have derived equation for internal energy and kinetic energy, which we derived from the total energy balance, and starting from the linear momentum balance we have derived equation for kinetic energy. So, now becomes very simple for us to almost write down the energy balance equation for internal energy. Okay. So, let us do that here, simple subtraction. So, we are back to the Lagrangian viewpoint. So, all our left hand sides will be once again will be in terms of d by dt. Only just 2 slides in between to discuss the significance of different terms in the kinetic energy equation, we went back to the Euler description. Okay. That is the differential energy balance equation for internal and kinetic energy. And this is the equation which we obtained for the kinetic energy from the linear momentum balance equation, and then we took this term and expressed as sum of 2 sets of terms, and now we will understand why we really did that. Okay. So, these are the 2 terms, this term and this term corresponds to this term. Okay. So, let us subtract this equation from this equation, the equation for kinetic energy from the equation for internal and kinetic energy. And so, the left hand side we will be left out with the substantial derivative of internal energy, of course multiplied by rho. So, now what happens, this term and this term cancels and this term and this term also cancels, that is why we express this as the sum of these 2 terms. So, that this term will cancel the same term in the first equation. So, now we have got a very simple equation, left hand side rho d by dt of internal energy, right hand side we have the heat input term, and then we have this term which is minus p into dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z. Okay. Now, let us look at the significance of the different terms in this energy balance equation for internal energy. Like we did for kinetic energy, we will express the left hand side back in terms of the Eulerian viewpoint, so that we can explain the significance of each term. I mean, with this also we can explain, we put in this form because we have explained the significance of all the conservation equations earlier in this form only. That is why, to be in line with those explanations, we are expressing the left hand side of the entire equation back in Eulerian form. Okay, so now let us take the left hand side. I think you should be able to write down the significance now very easily. The first term tells about time rate of change of internal energy per unit volume. Next set of 3 terms represent convection. So, net rate of flow of internal energy out by convection per unit volume. Right hand side, we are familiar with this term, net rate of internal energy addition by conduction. What it tells you is, because of conduction there is increase in internal energy, or because of heat input there is increase in internal energy. That is very much understandable. Now, let us come to the last term, which requires some discussion. We also have to discuss the importance of this term here and in the kinetic energy equation. Okay. What this tells you is, if you read this significance, rate of internal energy increase by compression per unit volume. How do you explain this? For that, we know this term as del dot V, but remember we also discussed this as the volumetric strain rate. Okay. What does it tell you? Fractional rate of change of volume. So, now let us say there is a decrease in volume. What happens? This term is negative and this will become positive, and that will result in an increase in internal energy. That is what this tells you. When I say there is decrease in volume, it means that we have compression. So, rate of internal energy increase by compression, of course per unit volume. Okay. So, just to repeat, those 3 terms put together represent fractional rate of change of volume, and if there is compression there is decrease in volume, that term is negative. So, the entire term becomes positive, it adds to the internal energy, and that is why this term tells you rate of internal energy increase by compression per unit volume. Now, let us look at the corresponding term in the kinetic energy equation. If you look at the 2 terms here it is minus P del dot V, and here it is minus P minus del dot V. Okay. Let us take the same case. Let us say there is decrease in volume, this term is negative, this entire term is positive. Now, what will happen in the right side of the kinetic energy equation? It will be negative, which means that the increase in internal energy is because of a decrease in the kinetic energy. That compression adds to the right hand side of the internal energy equation, it results in subtraction in the right hand side of kinetic energy equation, which means that there is a conversion of kinetic energy to internal energy. Now, not alone this, the other way can also happen. What is that? Let us say there is expansion. What will happen? This del dot V will be positive. So, it will be, the whole term will be negative in the internal energy equation. So, it will result in reduction in internal energy, correspondingly there will be increase in the kinetic energy. So, now this term becomes very clear, rate of conversion of kinetic energy into internal energy per unit volume. We can explain the significance only after deriving the equation for internal energy. That is why we postpone the explanation for that particular term. Also like to mention that because you can have either compression or expansion, and so there could be conversion of these 2 energies in both the directions. That is what we have seen. It could be internal energy to kinetic energy, or it could be kinetic energy to internal energy. So, more formally we call this as reversible conversion of kinetic energy to internal energy. So, what you have seen now is arrived at the differential energy balance equation for internal energy, expressed that in the Eulerian form, and then looked at the significance of the different terms in that equation for internal energy, and also specifically one term which appears in the internal energy equation and the kinetic energy equation with opposite sign. We have discussed the physical significance of that term as well.